We are working now on this mechanism, store-operated calciumetry. I wrote where because I think that the site of store-operated calciumetry in skeletal muscle are still, they haven't been identified before we did this work, but there is a lot of controversy about our findings. And I'm going to try to convince you, as Clara tried, that electron microscopy is still important to find something new in muscle, even if during my career always people look at us a little in a skeptical way, thinking that, you know, electron microscopy is such an old technique that we should move on to something else. But I still think that we can find new things with this technique. Calcium handling in muscle is the result of many different processes. For many years in Clara's lab we worked in studying excitation contraction coupling, so when the fiber is depolarized, there is an interaction between these two proteins, DHPR and RYR, calcium is released, and this release of calcium activates muscle contraction. Then the calcium that is released is quickly removed by the Cerca pumps that brings it back into the sarcoplasmic reticulum, and this relaxes skeletal muscle fiber. Then there is an amount of calcium that enters the mitochondria, and there is a lot of discussion, as we found out this morning, about how much calcium enters the mitochondria. Some people think it's a lot. We mostly think it's not much. But this calcium is definitely important to activate aerobic production of ATP. But when muscle is very active, probably there is part of the calcium that is lost in the extracellular space, is pumped outside. So when muscle is stimulated for a long time, it's possible that the amount of calcium in VSR is reduced a bit, and we talk about SR depletion, and this one could be one of the mechanisms that is responsible for muscle fatigue, for some reduction in muscle performance. And when there is a lot of SR depletion, there is another mechanism that gets activated, which is called store-operated calciumetry. So there are two proteins that are involved in this mechanism. One is a STIM1, which is a sensor in the lumen of the sarcoplasmic reticulum, which interacts with ORI1, it's a channel that activates when it's coupled with STIM, and this calcium comes back into the fiber, and this is important to replenish then the sarcoplasmic reticulum. So store-operated calciumetry has been described in skeletal muscle not many years ago. The first report was by this group of Ogawa in 2001, then there was a lot of work done by Lonnie Conis and Eduardo Rios, the first paper being in 2003. What we know now about store-operated calciumetry is that abnormal SOCI contributes to muscle dysfunction. Mutation in STIM1 and ORI1 are linked to a myopathy, tubular aggregate myopathy, and you're going to hear a little bit about this by Simona Boncompagni immediately after me. And then we know that SOCI is the short version of store-operated calciumetry, limits muscle fatigue. And for a few years it has been proposed that store-operated calciumetry occurs at the same junction that takes care of EC coupling, the triads, and you've heard about triads about Clara Franzini Hamilton. And however, this hypothesis never convinced us. Well, never convinced me, because we have been studying with Clara this junction, and this junction is very crowded by many proteins, RILD receptors, which are very large and they are tightly packed in ordered arrays. And I always thought, well, maybe there is no space really for STIM1 and RI1 to float around the membrane and meet each other to make store-operated calciumetry work. So this is the triad junction, and this is the site of EC coupling. So I thought maybe this is not really the site of SOCI, but for many years we didn't know how to try to find out where store-operated calciumetry was really occurring in muscle. But then sometimes people are lucky, and I was lucky to have in the lab these two guys here, Simona, that will talk shortly after me, and Antonio, that had the idea that changed the approach toward this project completely. They decided, since store-operated calciumetry, it may be important in muscle fatigue, they did something that now to me is very obvious, but they thought about it, I didn't think about it. So what they did, they decided to exercise the mice, to fatigue mice on a treadmill. Here you are seeing the mice running at this low speed. This is only the warm-up, but then they did an incremental running protocol of about 1 hour, going from 10 meters to 25 meters per minute speed. So they fatigue the mice. And then they fix the muscle in control animals and in exercise animals after this hour of running. And they immediately found the first striking result. If you look at the sarcoplasmic reticulum here in this area between one triad and the other triad, in this that is the eye band of the sarcomere in proximity of the Z line, the membranes in control muscle looks like this. They are very convoluted, they are tubes. But then after the exercise, the situation completely changed. In many points in the fiber, they found that the membranes here, after 1 hour of exercise, they were completely changed shape. They formed these flat stacks of cisterna. And this is very specific to muscle after exercise. So I will go fast in this first set of data because many of you already saw this, but then I want to stop more about the second part of the talk to the new data. Anyhow, what Simona did was actually using one of the protocols that Clara uses in her lab, using ferrocyanide that is put outside the fiber and enters the fiber, the ferrocyanide, through the transverse tubules. And what we discovered is that this remodeling of membrane induced by exercise was not only remodeling of the sarcoplasmic reticulum, but was also a remodeling of the transverse tubule. The transverse tubule, after exercise, would elongate from the triad into the eye band to make contacts with this vesicle of SR and with the flat stack of cisterna. These two images are in longitudinal section, while these two images again are in a cross section. You see the transverse tubule elongating here. And the fact that it's black is a direct demonstration that is in contact with the extracellular space. And sometimes we are lucky enough also to see one transverse tubule elongated directly from the triad and makes contact with this flat vesicle that now Simona has stained in green the transverse tubule and in yellow the SR. And this is the quantitative analysis showing that after exercise the amount of transverse tubule at the eye band is much more than in the control. So I went ahead and did some immunofluorescence staining for the two proteins of interest for us at this moment, which were STIM1 and ORAI1. I know this is a fairly complicated figure, but on this side you have the situation in the control, on this other one you have the situation after 1 hour of exercise. I wanted you to look at, well, we use the rhinodeceptor as a reference mark for the position of triads. So you see that here that STIM is not at the triad in the control muscle, while ORAI is in correspondence of the triad. ORAI is the protein of external membrane, so it is in the transverse tubule, and it's normal that it's colocalized with ROIR1. Indeed, we have a lot of yellow, which is the superimposition of yellow with green, but the most important part is down here. So in control muscle, STIM, which is in red, and ORAI, which is in green, they are not together. So the two proteins that mediate stauroparetic calcium membrane in control muscle, they are not really coupled to each other. But the situation changes completely after exercise, because after exercise now here you see a lot more green than here. So some ORAI moves into the eye band, which is this narrow space here, and now here you have a lot of colocalization between STIM and ORAI after 1 hour of exercise in those muscles in which we had the formation of these new junctions. So we were very excited about this, and we went ahead and did some functional studies in which we dissected the muscles and we exposed the muscle to repetitive stimulation. And now here you see the difference of behavior, functional behavior between the muscle that was exercised and the control muscle. In presence of extracellular calcium, the muscle that was pre-exercised and they had the new junction formed now is much more resistant to fatigue than the muscle of control. Does this depend on the usage of extracellular calcium? Then we did this experiment in which we removed the extracellular calcium and also we used blockers of stauroparetic calcium entry. Now if you see in the control, when we remove external calcium or we block the entry, now the drop in force, there is some drop in force, but it's not that much. But there is a lot more drop in force in the muscle that was pre-exercised. And this is an indication that this muscle that is most resistant to fatigue is using external calcium.
Can I ask something right now before I forget? The pre-exercised mice, what is the time frame between the first exercise and the second, please?
Okay, the mice were exercised and immediately sacrificed. The time they went from the exercise and then the fixation for electron microscopy, or this experiment is less than 1 hour.
Okay, but these are the pre-exercised mice.
Yes. So we pre-exercise the mice, we sacrifice the mouse, we take the muscle, we put it in the chamber, and we do the experiment before 1 hour.
That you were doing two, doing exercise, pre-exercise.
This is an isolated muscle from the mouse that was pre-exercised.
Okay.
Okay.
Thank you.
So we were very excited about these results because we thought we have found the sites of store-operated calcium entry. I have to tell you that the reviewers of the paper were not as happy as us. So we were stopped. The publication was stopped in many journals. So we managed to publish this in scientific records. So, but we also Simona drew this model of what's happening. So during exercise we have elongation of the transverse tubule from the triad toward the eye band and the remodeling of DSR forming these flat stacks. And in green and red you see the two molecules that should interact during store-operated calcium entry. And so we thought these are the site, our conclusion that this could be the site of store-operated calcium entry that assemble dynamically during exercise. So we published this paper, but we don't have many people that are convinced of our findings. So we are doing now new experiments, two sets of experiments. In the first experiment, we are measuring manganese quench. It's the technique that is considered the most direct measurement of calcium entry from the extracellular space. So the extracellular calcium is substituted with manganese, which is a divalent cation, and then during stimulation, when manganese enters into the fiber, you have inside the fiber you have FURA2, and FURA2 that fluoresces when it combines with calcium. When it combines with manganese, the fluorescence decreases. So if you put manganese outside, when manganese enters, you have the quench of fluorescence. And Antonio Michelucci went to the lab that can do this type of experiment. He's spending 2 years there in Rochester. And he did this fantastic measurement in which he sees that the manganese quench in exercise muscle is more than in the control muscle, and also this quenching of fluorescence is not present in mice that have knockout of RI1, meaning that the entry of this manganese into the fiber is through ORI channels. And so this was kind of stronger indication that what we are seeing is really store-operated calcium entry. And then now we are doing the last set of experiments. The last set of experiments, we hypothesized that if these new junctions that we think are the site of calcium entry, indeed we call them calcium entry units, if they assemble during exercise, they should disassemble following recovery. So what we did, we started to determine the time course of disassembly of calcium entry units following exercise. And what we did different time points. So the control, experiments done less than 1 hour after exercise, and then 6 hours and 24 hours after exercise. And we determined the presence of these structures here, so the stacks of SR systemic, and we determined how many we have. Different type of analysis, and you see that these stacks actually they keep increasing in number up to 6 hours after exercise, and then the numbers goes back to pretty much the control numbers after 24 hours. So this structure disassembled pretty much in 24 hours. But then we did the technique with the staining of the transverse tubules now. Now the transverse tubules are stained, and you see them here, making contacts with the stacks of SR system. And what we found is that the time course for the transvertebral is much faster. Transvertebral are much increased, less than 1 hour after exercise, but 6 hours already their number is going down and it goes down to normal after 24 hours. And this is the amount of transvertebral at the high band. So we did also the experiments of manganese quench, so the function. And if you look at the function, we did 2 sets of experiments in presence of SR depletion, depleting the SR, and then doing the experiments. And this is also in absence of SR depletion, and only in the experiments that are done less than 1 hour after exercise, which is the time in which the transvertebral is still elongated, and the transvertebral contains ORI1, we have greater manganese quench, so entry of divalent cations from the extracellular space. So from this data, what we can conclude is that this calcium entry units disassemble following exercise. First, we have retraction of the transvertebral from this junction, while DSR stacks are a little bit more stable. And then in 24 hours, the transvertebral is all retracted, and also DSR goes back to the initial shape, and also this stacks of membrane disappears. So plasticity of transvertebral is greater than the plasticity of DSR, as the transvertebral retracts faster. And also what's important is that once the transvertebral are retracted from the high band, so here, really also the rate of manganese quench decreases to control levels. And now if you look at the time course of transvertebral elongation and the time course of the rate of manganese quench, they are perfectly comparable. And this is telling us that the transvertebral elongation during muscle activity and the association with these stacks of SR membranes is really the key mechanism that allows the formation of functional calcium entry units, which is, if we are right, this is a new organelle in muscle that assembles dynamically during exercise, when muscle really needs to take back some of the extracellular calcium that is losing during prolonged muscle activity. And I hope we are right. We are submitting now the second paper with this, the story about the time course of this assembly of this unit, and also the story containing the manganese quench. I hope this time we are going to be able to convince our reviewers. And to conclude, I would like to use this slide that was borrowed to me by our friends Larson. The 3 stages of truth. At first it is ridiculed, then violently opposed, and finally becomes accepted as self-evident. So I hope we're going to be able to convince people that store-operated calcium entry occurs in this new unit called calcium entry units. And I thank the people that work on this job and all of the granting agencies. Thank you.
If you have ever looked at myotonia or myotonic muscle, so I'm guessing if your hypothesis is true, in that kind of muscle that are not able to relax, maybe you will find your store-operated calcium entry structure more often. I mean,
anyway, never look at that muscle. We have found these structures several other times. In the past, we actually ourselves described them wrongly because we were describing them as SR stacks at the time in which we didn't know what they were. And in models in which there is calcium unbalance, for example, our calsequestrin 1 knockout mice, which have no calsequestrin, and the SR, as shown by Carlo Reggiani, is always depleted. There are many of this junction, and probably our calsequestrin knockout mice survive because they are using continuously external calcium. They are pre-assembled from constitutively pre-assembled. So these mice use external calcium continuously. I've never used. This is a very good suggestion. If I have a chance, I will look into it.
I'm just curious. You exercise the mice for an hour. Is that? And I'm not familiar with exercising mice. How extreme is that?
The mice are fine. The mice are fine. There is not a lot of muscle damage. No.
It's
Most of them complete the experiment without even stopping. Some of them stops in the last 5 minutes, but just tired like me and Marco when we go running, right? So also we can get tired too. So it's nothing really dramatic for them. They're perfectly fine, and we don't see what.
They only go like that.
Yeah, well, they're sweating. Yeah, but they keep running. Yes, please.
This is adaptation to exercise, but why it's so long lasting? If you start running, it takes about upregulation 6 hours and then 24 hours to be reduced once again. So I don't think it's only exercise-dependent adaptation. It's for me a little bit too long.
I don't know. Well, we still cannot explain why this SR stacks keeps assembling for 6 hours. Transverse tube retracts very quickly, while the SR stacks for 6 hours increase in number and then they start decreasing. I think I'm going to get some information into that. We are doing now, instead of doing a single bath, we are training mice continuously and see if long-term training really creates structure that are more stable in time. So I don't know about this question. I mean, it's a good question, and I had to come up with an idea for this. Yeah.
Have you ever measured after 1 or 2 or 3 hours? Because after 6 hours, this is...
Yeah, no, we haven't done other time points. Yeah, maybe
You killed your experiment. They die.
Yes, I don't know.
Have you had the opportunity, Feliciano, to look at calcium transients with this new structural arrangement?
Oh yes, yes. I have the slides here. We've done everything. Once you get this structure assembled, you have better recovery of external calcium, and the transient can sustain themselves better. We do have those data, and I will try to find them in my computer. They're not in the presentation. So we have done this. So I will show you the traces that Antonio collected with transients.
One last very brief question.
A short one. Do you have any difference between slow twitch and fast twitch muscles?
Yes. So this was mostly fast twitch. Simone is working in doing the same structure in slow twitch. They're a little different. One transverse tubules make a contact with a single SR, while we don't understand yet why in the fast twitch the SR makes multiple stacks. Okay, by similar, just that we don't have those multiple stacks of SR, but a single SR with a single transverse.